When you ask an autonomous coding agent to complete a task, you want it to persist until the job is done. Developers designed the /goal command to do exactly that, forcing the model to keep looping, checking its work, and trying harder until it succeeds. But on complex mathematical optimization tasks, applying that exact persistence mechanism backfires. Giving a model more time to try harder actually makes its final output worse. To understand why, we are looking at how two of the most capable models available, Claude Fable 5 and GPT-5.6 Sol, handle an impossibly hard task. This chart compares their performance with and without the goal command. At first glance, the persistence feature looks like a success. It won 4 out of 6 head-to-head trials against a standard prompt. But look at the resulting trend line representing the mean scores. That high win rate hides a severe performance penalty. When forced to persist, Fable 5's average score dropped by 759 points. Sol's average dropped by 868 points. These are verified results from Charles Zam's operations research benchmark. He tested these models on a network design task, where lower scores are better, and found that telling them to try harder caused their average performance to degrade. A feature built to guarantee task completion becomes a liability in an infinite search space. To see why, we have to look at the math behind the problem they were trying to solve. The primary test is the Curo benchmark, a high-stakes operations research problem centered on physical fiber network design. The solver receives a map of distribution hubs and terminals. Its objective is to connect them all while minimizing the total length of cable used. It must do this while navigating strict structural constraints. The network requires redundant loops, short-hanging branches, and every single tower must appear exactly once. Scaling a problem with these constraints triggers a combinatorial explosion. The number of valid networks multiplies so rapidly that brute force calculation becomes physically impossible. This diagram illustrates the baseline parameters for the city of Paris. We have exactly 11 distribution hubs and 532 terminals. If we deliberately restrict the rules to calculate a strict lower bound, allowing only 19 loops of 28 terminals with no branches, we get this equation: 532 factorial divided by 19 factorial multiplied by 11 to the 19th power. That yields a search space of roughly 10 to the 1,223rd power. In a massive search space of that magnitude, an AI agent simply cannot iterate its way to the correct answer. The outcome depends entirely on the strategic direction of its very first decision. Since initial strategy is the only thing that matters, we must look at how Fable and Sol actually execute a persistent goal under the hood. Claude Code implements the goal command as a session-scoped stop hook. After the main agent completes a turn, a secondary system intercepts the loop. Claude outsources the judgment to a smaller evaluator model, typically Haiku, to determine if the objective is complete. But Haiku operates with a critical limitation. It cannot inspect files or run diagnostic tools. It judges progress based purely on reading the conversation transcript. Codex uses a radically different architecture: persisted thread state. Instead of an external judge, Codex relies on an SQLite database to store the objective's status and budget accounting across the lifespan of the task. The primary working model is given specific tools, allowing it to manage its own lifecycle. This means Claude relies on a blind judge reading a text transcript, while Codex allows the primary working agent to grade its own homework. On a standard coding task, like fixing a broken unit test, progress is legible. A passing test provides the clear evidence needed for these systems to recognize completion. NP-hard optimization tasks offer no such feedback loop. This makes it impossible for verification methods to distinguish between a genuine breakthrough and a dead end. These systems measure the duration and intensity of the effort applied. They cannot calculate the mathematical validity of the actual search trajectory. We see the cost of that failure in the raw data from the 30-minute matched runs. This scatter plot shows Claude Fable 5's baseline performance without the goal command activated. The stability is immediate. Fable 5 stayed within a remarkably precise 319-point range. Compare that to GPT-5.6 Sol's plain baseline. Without a persistent goal, Sol's performance is highly volatile. Its results span a massive 1,958-point spread. Now introduce the goal treatment data. Providing a persistent loop degrades the average score for both models, pushing their center of mass higher up the chart. Fable 5 presents a strange anomaly. Activating the goal command produced the single best clean score of the entire test, but it simultaneously dragged the model's average down. While the plain mode never achieved that single absolute peak, it remained the mathematically safest configuration for both models. A persistent goal loop does not generate better ideas. It simply provides a larger computational budget for the agent's first idea to mature, whether that idea is brilliant or completely broken. We can visualize what happens inside the black box when an initial strategy is granted limitless persistence. When Fable 5 built a highly efficient compiled portfolio, the goal command successfully amplified that good decision. It sustained the correct strategy and drove the score to the absolute peak. But when Sol committed to an exhaustive anchor sweep, the goal command forced the agent to waste time executing a mathematically doomed strategy. The agent falls into a local minimum. It finds a flawed path that it stubbornly perceives as progress, and burns its entire budget trying to dig deeper into a dead end. On a complex problem, the duration of an agent's loop matters infinitely less than the baseline quality of what that loop keeps doing. As we design systems that govern their own compute budgets, we have to ask, are we optimizing for the smartest solution or just the most stubborn one? Navigating an infinite search space requires the wisdom to identify a failing strategy and stop.